All right, moving into 10.5. I've already made videos for 10.5. I made them last semester, but this is when I first started making videos. The quality is horrible. You can barely hear me. I was younger, not as wise and as I am now, so I'm just going to have to remake them. So here we go. So 10.5 is, 10.5 is a very big section, so there may be a few videos here for 10.5. Starting off, we're going to talk about something called absolute convergence. And before we get there, let me just kind of write out a couple of different series. So let's look at this series, 5 minus 5/4 plus 5/16 minus 5 over 64 plus, and then forever and ever and ever. If we wanted to write this in our notation, this would be the series n equals 0 to infinity, two infinities, of 5 times negative 1/4 to the n. And this should look familiar, right? This is a geometric series. You have your constant a, 5, and then your r value that you're multiplying over and over and over again, negative 1/4. This, by the way, converges since it is a geometric series with our r value negative 1/4, and since that absolute value is less than 1, we converge. Okay, let's look at another series. It's the same series, but instead of it alternating positive, negative, let's look at just all of the positive values. This would be very similar. It'd still be n equals 0 to infinity, but 5 times positive 1/4 to the n instead. This is also a geometric series that converges. It's just that this time the r is positive 1/4, but still it's less than 1 as an absolute value, so it still converges. We need to talk about the difference between these two series. One of them is alternating positive, negative, positive, negative. The other is just positive all the way down. So we're going to look at some definitions here. Absolute convergence first. Okay, so just as a definition, a series converges absolutely if the corresponding series, the absolute value of the sequence a sub n converges. Okay, so we are going to see examples of series that converge when they alternate like this, but do not converge when we're just looking at the positive terms. This example, on the other hand, this is an example of something that converges absolutely. It converges absolutely because not only does it converge when it alternates positive, negative, but it also converges when it's just all positive terms the entire way down. So again, this converges absolutely, but that's not always going to be true. We will see examples of ones that converge when it alternates, does not converge with just positive numbers. Okay, from this definition, we do have a theorem. That theorem says if the series of the absolute value of a sub n converges, then we automatically get that the series of just regular a sub n converges. Okay, so what this theorem is saying is that if you have something with only positive values, if only positive values converges, then you can put as many negative signs on those values as you want, and it's still going to converge. Okay, so if something converges like this, with all positive, then we automatically get that the series without the absolute value also converges. Okay, I have a proof for that, but I'm not going to bother writing the proof out in these videos. So skipping over that, let's just look at a good example. So here's our example. We're going to look at the infinite series in going from 1 to infinity. Oh, sorry, there's that button again. Should be a drinking game for every time I hit that button. Negative 1 to the n plus 1, and then 1 over n squared. Oh, jeez. Like this. Okay, great. So negative 1 to the n plus 1, and then 1 over n squared. If you want to see what this series looks like, just plug a couple of n's in there. If I plug n to be 1 in there, I get 1. Minus if I plug n to be 2 into there, I get negative 1/4. And then you just keep going, plus 1/9, minus 1/16, and then forever and ever and ever. So it would just alternate positive, negative all the way down, and then it'd be 1 over these perfect squares. Okay, so there's not really a question to this one. I just want to kind of look at this example and then really break it down as far as we can break it down. Here we have this alternating series. The question I guess you could ask yourself is, well, does this thing converge? We don't even have to think about it too hard, because if there were not alternating, if these were just all positive numbers, then it would just be the series 1 over n squared, which would be a p series. So if we think about the series, so just the series 1 over n squared, which would be the absolute value of the series, this converges because it is a p series, with p being bigger than 1 because p is 2. Now, since the series 1 over n squared converges, then we automatically get that the series above, I'll just copy it, converges. All right, so that's just using the theorem that we just wrote down here. If the absolute value of something converges, then you automatically get that that thing, that series itself converges. So that's all that that's saying. Okay, so now let's jump down into probably the most important thing that we are going to look at in this section, maybe even the whole chapter, and this is something called the ratio test. So the ratio test is kind of building on this absolute convergence. I will go ahead and tell you now that the ratio test is probably the most useful tests of all of the tests that we have, the nth term test, integral test, and the comparison tests. Ratio test is going to be the main one. So let's look at the definition for it. Let there be a series, a sub n, be any series, and suppose that you look at the limit of that series, not just the series, sorry, we're going to make it a little bit more special than that, but the limit as n goes to infinity of the absolute value of the n plus 1 term of the series divided by the nth term of the series. Let's say you do look at the limit of the next term divided by the previous term's absolute value, and that came out to be some number. So that thing we usually call this Greek letter rho, you could leave it as p if you want. That's all that the Greek letter rho is a fancy looking p. If this is the case, there are 3 possible outcomes. The first outcome is that the series converges absolutely as long as that rho is less than 1. So if you look at this limit of these sequence values, absolute value, and this comes out to be a number less than 1, then you get this really powerful statement that the series doesn't just converge, but it converges absolutely, which is a lot stronger. On the other hand, the series diverges if that rho is greater than 1, and then the test is inconclusive if the rho is equal to 1. Okay, so this is the ratio test in a nutshell. If we have a series and we look at the ratio of the n plus 1 term of the sequence divided by the nth term in an absolute value and take the limit as that goes to infinity, this is going to come out to be something. If that something is less than 1, then the original series converges absolutely. If that something is greater than 1, then the original series diverges. If it comes out to be exactly 1, then the test is inconclusive. I have a proof for this as well, but I'm not going to write it all out. Look it up in the book if you were curious about the proof for the ratio test. In the next video, we're going to do a bunch of different examples of this because these can get a little bit complicated.